Good evening, ladies and gentlemen. Thank you very much for giving me a screen and voice. My topic would be microbial hydrogen production, recent achievements. And my name is Gawel Solosky. I'm from my talk today is about this, how hydrogen, why we need to operate on hydrogen, because we have few time to replace conventional method, oil, gas and coal, and we need to utilize our wastes, and therefore we have to find method to close the loop, so we use our waste again, transfer into useful material, and one of the methods is closing the loop is using microbial potential microbes like dark fermentation, like Clostridium, like algae, like fungi, to prepare organic waste, to convert it again to valuable product, to polymers, to fuels, and to chemicals for continue our lifestyle. As we see, here we is closing the loop is two types of organic waste coming from biocenosis, from plant and animals used by man, and other is fossil origin, so from fossil fuels, because fossil fuels are also organic waste which were accumulated by billions of layers by Earth and now are excavated and burned. So again, we use all the absorbed by Earth carbon. So fossil origin is plastics and carbon dioxide, which we can use also mixed with some biofuels for poles. Of course, plastic with this lignocellulose can be mixed in the form of pyrolysis, but this thermal method not including microbes can be used as prepared lignocellulose available for thermal decomposition of polymers. Other ways is to prepare biofuel by applied plants, so algae and fungi applied animal, so scare proteins for animals, and even some worms to bioabsorb some toxic material, and then after this, these plants can be by bacteria transformed by dark fermentation or anaerobic digestion, and these plants, lipids, can be then used as biofuel source. And this shows us that we coming by applied plants. I might have combining micro and macroalgae as compared with other method, and this make available to closing the loop. This shows availability of our wood. Here we have the difference comparable how in 5 years' time we develop the 5 different microbial decomposition strategies, such as dark fermentation, biophotolysis, photofermentation, microbial electrolysis cell, and aerobic digestion. In 2018, in case of dark fermentation, we're thinking about only hydrolyzed and sugars. Only with some trials in fats, and proteins were only theoretically. Was on that we can mix with asbestos. Now, in 2023, we don't use single matter, single feed, homogeneous feed. We use check heterogeneous. We mix sugars with hazardous material as asbestos. The genetically modified bacteria can omit limitation on dark fermentation is only 33%. The proteins becomes also potential feed. So we see big increasing of variety. In case of biophotolysis and algas, we have concerning mostly as hydrogen and sometimes on pharmacy. Now, in 5 years' time, their big advantage is absorbing much of carbon dioxide. So we can reduce greenhouse effect, and remove some biosorb some metals. So wash our wastewater from metals, and sell all the lipids used as base to liquid oils, or then as the rest after using as the feed of dark fermentation, photofermentation, and aerobic digestion. The rest are also possible to be made biopolymers. Similarly, like low bottom product of dark fermentation is polyhydroalcoholates, which like polylactate, for example, which can be also raw materials for polymers. In the case of microbial electrolysis cell, in 2018, we only were looking about water splitting. So only we considering mostly water as potential feed, but water wasn't independently from bacteria to be splitted. There needs extra charging. Now we found that butyric acid is possible and ammonia. So give some compounds that can be split into hydrogen without extra charging. The photofermentation will also be combined because as supplementary, because the only metal has big variety of waste, bigger than dark fermentation, and can use this organic acid. Organic acid can be used after dark fermentation by photofermentation and anaerobic digestion or microbial electrolysis. So these all 4 can be combined into one plant to make very high conversion of every of these processes. Here that's how it's going from our dark fermentation to anaerobic digestion, and we did the difference that stop of acidogenesis. If, of course, in case we have not genetically modified bacteria, and here we have mutagenesis. So here are some medical problems. We have natural case of dark fermentation, which is gangrene and tooth decay, because bacteria like sugars for also this dark fermentation. And in case of teeth decay, if undigested sugar land of your teeth, then will bacteria eat this, destroying your teeth and collapse. This is the example of hydrogel production in your teeth, and that's why you collapse. And in case of gangrene, which also bacteria for dark fermentative bacteria causes, It was case that in Henry VIII, the King of England, in 16th century after burial, his body collapsed and exploded due to this hydrogen. So, conclusion, we need to think that more simpler matter is occurring waste, like potato starch, the less needed is pretreatment is cheaper, and hydrogen will be much effective. But not much waste is for starch, so we need to conclude common waste with very efficient waste for hydrogen, and this combination is key in designing of our processes. These are some references. Thank you very much.